this one? We did this one? We've got one example left. All right. Yes, we did do that one. And this one I wanted to do because this is what I expect you to do in your textbook. In your textbook, you'll have a derivative question. And then you'll look at the back of the textbook, and this will be the answer. And your original answer may look nothing like that. So we have to use our algebra to get it to look like that. So, first of all, the first part of this question says, start with y. We want to show that the derivative is equal to that. So first of all, I look at my equation. I was tempted to go right to my derivative, but I'm going to take the time to change the x to x to the half. And then we analyze the question to see what we have to be prepared to do. So right now, I see two things multiplied, and both of them have x's, so my product rule will be here. Then, in the two things that are multiplied, in the second one, I see that I have a function inside of another function, so the second one will have a chain rule. So in our mind, we think, okay, product rule is keep one the same, derivative of the other one, then keep the second one the same, derivative of the first one. And the chain rule is derivative of my outside function, keep the inside the same, then derivative multiplied by the derivative of the inside. So we have that in our mind, and we start our derivative. Starting with the product rule, keep one the same. Multiplied by the derivative of the second one. Well, the second one is a chain rule with the outside function being the 2, so I bring the 2 out in front, subtract 1 from the exponent, keep the inside the same, then multiply by the derivative of the inside, and the derivative of the inside will be negative 1. Plus, keep the second one the same, and multiply by the derivative of the first one. And we have our answer, and we look at what the show that is, and it is not even close. So how do we use the answer to guide us to getting, or to guide us to know what to do next? So a couple of things. First of all, I see that the answer has a square root in it. I also notice the answer has a fraction. So what I'm going to do is I'm going to change all my x to the halves. Back to square root. So that x to the half would be the square root of x. I put the 2 out in front, just sort of proper order of writing things. Oh, times by negative 1. I'm going to, instead of a 2 out in front, you can see that that would be a negative 2 out in front once I combine everything from that first term. And in the second one, we would have plus 3 minus x squared. And I would have that x to the negative half is a square root on the bottom, because the negative exponent would move that x to the half to my denominator, and then the x to the half becomes a square root. So I have a square root on the bottom. So first of all, looking at what the answer was, I saw the square root, so I decided to change all of my x to the negative halves back to square roots, and I got this form. The good thing about this form is I do have a 2 root x on the bottom, and I want a single fraction in the end. So again, analyzing where I'm at, I notice that I have, this could be over 1, I don't have a single fraction. I'm adding 2 fractions right now. How do you add fractions? You need a common denominator. That common denominator, we want to be that 2 root x. So I'm going to multiply this by 2 root x on the top and bottom. That would get me a common denominator. So I have my common denominator, 2 root x. When I multiply up here, I'm going to get -4. Root x times root x will become x. Times by 3 minus x. And I will still have plus 3 minus x squared. So one thing that you would be doing in a show that question is, because the answer should be guiding you, you're sort of like, okay, now I got that 2 root x on the bottom. I go back and look, oh, the top is factored. So I need to work with that a little bit, okay? But my bottom, my denominator now is good. I've got the 2 root x on the bottom. So now I just need to manipulate the top to get it to look the same, okay? Two options that you could do. My suggestion would be factoring right away, but you could, and what's probably most typical for you to see would be like, oh, I should multiply everything out on the top, combine my like terms, and then see if I can factor. That's perfectly fine, but in this case, you have two terms, and I hope you notice there's a 3 minus x in this one and a 3 minus x in this one. There's something common in both of those terms, so we can factor that out. And looking at what we want to show, has a 3 minus x as one of the factors. So I think this would be a really good idea to take out a 3 minus x. Out of the first one, you'd be left with minus 4x. And out of the second one, you'd still be left with 3 minus x. And now I can combine my like terms. Ooh. Is this what it's supposed to be? Yes. Because that's where you get nervous. You do the next step and you look and you think you got it and it doesn't match up, then you know you've made a mistake somewhere. This is a great show that question because it wasn't just one step to manipulate. We had to think, we had to use what we knew about square roots, negative exponents, adding fractions, common denominators, factoring. If you look at all of the skills from previous years that are built into the show that, this is really a good place to increase your algebra skills. Now, part 2 of this question said, find the x-coordinates of all the points on y equals square root of 3 minus x squared, where the tangent is horizontal. So we want to find out where the tangent is horizontal. In other words, your tangent line looks like this. This is going to become a huge concept in the units that are coming up, especially in our applications unit. But for right now, we haven't dealt with this very much at all. Okay? A tangent horizontal is when the slope is equal to 0. In other words, and if the slope of a tangent is what you get from your derivative, this is another way of asking, where is the derivative equal to 0? Because a horizontal tangent is a completely flat line. That has a slope of 0 because it has no rise, just a run. And that would be where our derivative is 0. So now what we can do is we can take our derivative equation, and here is why it was nice that we factored. And we have to solve this. First of all, okay, if you have a fraction, because this on the right-hand side is one big fraction, if you have a fraction equal to 0, just using numbers, think of 10. Okay, so 0 over 7 would work. 0 over 3 would work. 0 over 100, 0 over 16. If you think of 10 actual examples of fractions that are equal to 0, very quickly you'll realize something's in common. A fraction is only equal to 0 if the numerator is equal to 0. So you could just look at this and say, I only need to solve where the top is equal to 0. Algebraically, we could do this as well. If you have an equation with a fraction, you can get rid of that fraction by multiplying both sides by the denominator. And can you see that if I multiplied both sides by cube root x, this side would stay 0, and this side would be just left with that. This is nice, it's already factored, right? Although, guaranteed, sometimes you will not be thinking, you will multiply this out, and then go, oh, how should I solve this? It's quadratic, I should factor. And then you factor, and you get back to where you started from, only to realize, oh, I was there already, and I just spent 2 minutes doing math when I didn't have to. So if this is equal to 0, this first factor, well, it could be 3, and the second factor, x would be 3/5.